Um, Hi, everyone. Hope you guys are well. I miss my travels to Europe, especially. I can't wait till the pandemic is finally done so I can get back over there and visit many of you. So yeah, I want to talk about sort of the efforts we've been putting together on data-driven methods. I'm mostly interested in engineering and physics systems. And so a lot of what we want to do is start framing a lot of the machine learning methods around dynamical systems. And so that's the big goal here. I feature here Steve Brunton. He's my main collaborator. Mostly, we're going to feature the work of our postdocs and students. So we have a joint group with lots of great, talented people. And so ultimately, I'm just going to feature much of the work that they have been doing on this kind of this kind of topic. So let's get started. And also, I'll keep my chat open just in case questions are asked. Okay. So everything's going to start here, partly because I want to start thinking about physics systems. And I'm going to try to argue that essentially what we really need in a lot of this data-driven effort is ways to think about coordinates and dynamics jointly. So for instance, we're going to have input data. We're going to have measurements of a system. And just because you measured it doesn't make it the right variable. You measured it because that's what you had a sensor for. And so what we want to do, first of all, is start to learn what are the right coordinates in which to place the representation. We've been doing this for a long time. So for instance, we might use special functions. In fact, all these special functions like Bessel, Hermite, Laguerre came out of the geometry of various systems. And so partly it's to exploit geometry or exploit structure or special features of the coordinates so that you could write down your system in a much more advantageous format. You can also do this with expert knowledge. That's one of the advantages of having studying quite a bit in your field, is that you actually learn quite a bit about the system and maybe how you should place this. SVD-based methods are more an emerging technique in the last number of years, which really use this dominant correlated features of data to learn low dimensional representations. And by the way, this has many names: proper orthogonal decomposition, principal component analysis, empirical orthogonal functions, Hotelling transform. All of these were the same thing. So one of the things that I want to highlight here, that SVD-based methods, everybody reinvented this because it's such a powerful technique. And more recently, where we're really going to push this is learning neural networks. So learning transformations from your input data to a good representation. Now, once we get it into the dynamic variable that we want, the coordinate that we want there, we can start thinking about building models there. So we can do things like, now that we have time series in this coordinate system, then I can think about building things like ARIMA models. This is a statistical way of learning time series. Or there are different emerging methods like dynamic mode decomposition. So at Imperial, Peter Schmidt is there in applied math, and he is the originator of the dynamic mode decomposition. And this is a regression to a best fit linear dynamical system. And this is strongly related to Koopman theory, which is a broader theoretical construct around DMD. I'm also going to talk about just directly trying to discover governing equations in this representation. And this is called SINDy, which is sparse identification of nonlinear dynamics. Or we could try to discover normal forms. Or if you want to just go straight machine learning, you could have this time series and just say, well, I could just learn things like some kind of neural network like an LSTM or a data recurrent units, echo state networks, things like this that would allow me to learn a model for how the dynamics evolves in time. Okay, so first of all, I want to talk about what does it mean to have good coordinates. So, right, this is kind of a central concept here. And so good coordinates, I want to do this in terms of a story. So I like this story, I tell it a lot because I just feel like it really highlights everything I want to do. What you're looking at here is the retrograde motion of Mars, which is right here in the front. And this is the retrograde motion of Saturn. This is like the oldest physics problem. right? People were observing the night sky, trying to understand planetary motion and predict the paths of the planets. At the time this was being done, in the time of Ptolemy, which proposed the first theory for this, we believed we only had 6 planets. And so people wanted to understand their trajectories. So the first successful theory of this was called the doctrine of the perfect circle. It came out of Alexandria, Egypt, 2nd century AD, Claudius Ptolemy, who proposed that basically to understand the retrograde motion, it was a way of thinking about circles on circles. So that's this doctrine of the perfect circle. So there's a circle, and then there's a circle around that circle, and this would be able to basically characterize the motion of the planets. And in fact, this was widely adopted in that 2nd century AD, and it lasted for about 1,500 years. This is like the Roman Empire of theories. Very few theories will last this long successfully. But this is what happened here, is that it was 1,500 years before finally we had a theory to replace it. And this is really due to the pioneering works of Copernicus. And what finally closed the deal was really Galileo and Kepler, who pushed this idea and had the theoretical construct, and also Galileo having the observations of the moon motions around the planet Jupiter that established this as a viable theory, which was, if we change coordinate systems to a heliocentric universe so that the Earth and Mars are both just going around the sun, then the retrograde motion is just an observation in a moving coordinate system. So that was established at great cost to them. Galileo was forced to recant all of this and was in house arrest the rest of his life for proposing this. But it was because of this move to this coordinate system that 100 years later basically allowed Newton to formulate F equals ma. So we first needed the right coordinate system to then frame F equals ma. And of course, as we got better and better observations, here's something really important. Every time we improve observations, let's say by an order of magnitude, what we find is, and what was found, is that in fact, Newton's laws didn't quite hold. So at first they thought maybe there's a missing planet. That wasn't the case. And here in the early 20th century, Einstein was able to propose the theory of general relativity that explained the discrepancy between the Newtonian view of the world and what was actually happening. And most likely there'll be a picture on the right of Einstein. As we get better and better measurements, we will build more and more refined theories of gravitation. Okay, so here's the discovery paradigm. And this is the reason I just give this historically, is because I think it's just a concept for you to have in your head, which is what we have is observations from the Earth. And so we see another of the planets moving around. And this is again the Ptolemaic theory. But instead here, the coordinate transformation is supposed to learn for you the correct coordinate system, which is the heliocentric coordinate system. And then in that coordinate system, I want to learn the F equals ma physics. So that's what we're really going after here, is trying to use machine learning methods to help us through this process, right? It was 1,500 years between this step here to here, and then it was another 100 years to get this out, right? So we're trying to shorten the 1,600-year cycle of discovery down to a much shorter time frame, okay? Like on the time frame of a PhD thesis, let's say. All right, so there's also something interesting about Kepler and Newton, which is it reflects some deeper thoughts on how you do modeling. In particular, Kepler, one way to think about Kepler's theories of gravitation, or his gravitational laws, was of planetary motion, was that he actually had the elliptical orbits all worked out. And so when Newton wrote down F equals ma, and he constructs his solutions, they were just what Kepler had. Now, so why do we always talk about Newton in some sense as a more profound physicist? Because with F equals ma, there's something really important that can happen. Once you have that parsimonious representation of the physics, you could imagine with Newton's theory, launching somebody from Earth, putting him in orbit around the moon and bringing them back to Earth. whereas Kepler was a fit to the data. He did not have the ability to do an extrapolation. He interpolated. And this kind of, let's say, perspective or their legacy really is borne out here in modern machine learning, right? Which is, I want to give you two of the sort of state-of-the-art, the grand challenge problems today. One is robotics and one is the self-driving car. They're both autonomy, but in some sense, they both inherit different legacies. The robot, which is amazing, like you can see what this robot's doing. It's just unbelievably athletic. It inherits the legacy of Newton. That robot is built by physics. It has F equals ma knowledge, momentum, angular velocity, all of these key physics concepts. It has this in order for it to do control theory and stabilize its motion. Whereas the self-driving car is actually quite different. It is a bank of sensors and with learning rules. It has no physics knowledge, no inherent physics knowledge at all. It just has massive, massive training data, and that allows this thing to drive in very complex environments. Both methods, by the way, are quite successful. And so one of the things to think about, I'm not going to make any commentary about which way is better than another way, but I will say that I'm going to be up here more in the physics world. I want to be able to take data and build physics models. Here, this is more black box, and you can still be very successful with this, but I want to come up here and be up here. Okay, so let's talk about mathematical formulation. Here it is. So here's the ill-posed problem I'm going to give to you. You're going to take measurements, y of t of k. In other words, the measurements are specific time points. And when you measure something, you measure whatever your sensor measures. So it's not even clear that what you measure is the actual state space you're interested in. So the state space x, you first have to infer from the measurements what the right state space is. F itself prescribes the dynamics, and H itself is a measurement model, okay? So the goal here is to take measurements, from measurements, infer what the correct state space should be. So in other words, that's essentially identifying the right measurement model, and then also identifying the dynamics and their parameterizations, okay? All right. So that's the goal. And it's actually ill-posed. You can't actually do it. This is not a well-posed problem. And so at least from my graduate experience, when I was a graduate student, when someone said there's an ill-posed problem, you'd go try to solve something else because that means it was not well-posed. So you don't have a solution to this. What I've learned in data science is you say, well, if it's not well-posed, then apply some constraints or regularizations, right? And once you've done that, pose enough of these to make it well-posed. So go from ill-posed to well-posed by applying constraints. And here's the constraints we want to apply to this to regularize this. Interpretability and parsimony. This is what, at least for me personally, I think is really important for the physics design process. And the idea of, and I'm going to explain what this means as we go along, you'll start seeing this, but I want a nominal model of the physics. And this idea of a nominal explanation goes all the way back to William of Ockham and the idea of Occam's razor. So Occam really was trying to advocate for use as few explanatory variables as possible and no more, okay? Pareto also really pushed this idea of a Pareto frontier. So these are just two people who have, and this idea of nominal models has been advocated over and over again throughout history from various scientists, okay? And so the idea here is to say, how do I regularize this by having as few number of terms and also sort of in some sense, the right compact or low dimensional representation to put everything together into this nominal representation. And those are going to be the regularizations to turn this ill-posed problem into a well-posed problem. Okay, so I'm going to start off here by building linear model. So if I come back to here, I'm going to say, well, could I discover a coordinate system in which the dynamics F is actually just prescribed by a linear model? Okay, and in the linear models, what's nice about linear models is that they're easy to solve, right? If you have a linear model, you just find eigenvalues, eigenvectors, and you're done, right? It's very easy to solve these if you have a linear model. So this is this idea of Koopman embeddings, which is to say, I want to go ahead and take a nonlinear dynamical system. Here it is, for instance. And if I can, one way to do this is of course, you can simulate this. This is a pretty trivial example. But another way to do this is to say, well, if I can find a different coordinate system, here it is, y1, y2, y3, which is x1, x2, x1 squared, then this system is linear. So now the linear system is trivial to solve, right? You just write down eigenvalues, eigenvectors, and then I can just tell you what the solution is at any time for any initial condition without actually having to run a differential equation solver. I just write down the solution for you at any point. So there's a compelling reason for linear models is because they're easy to solve and linear superposition holds. Okay, so this is this idea of what we want to do here. And this relates back to the dynamic mode decomposition and also Koopman theory, which is I measure a system, okay? And it could be, for instance, some spatial temporal system or high dimensional system. X is this unknown system. And from the measurements, I can construct data matrices. And these data matrices, the way I think about X and X prime is X is a series of snapshots of the system, and X prime are all of those snapshots advance delta t into the future. So what DMD does, it just simply says, oh, I want to find a linear operator that best fits all of these snapshots moving delta t into the future. So an easy way to do this is just with a least square regression, which is to take a matrix A, which advances me from X to X prime, and do a pseudo inverse, and you're done. I now have a linear model approximating the system. And what's attractive about that, it's really easy to do. And now you have a linear model, okay? Or you can come this other way, which is Koopman, which says, well, I don't have to work directly with the data matrices. I can work with functions of the data matrices. In other words, I can take and think about not just looking at the data itself, but let's say the data, the square of the data cube. I can look at different features of that data and build new data matrices y prime, which is in an enhanced space in some sense. And then I can do the same DMD process, but now with these augmented variables. Okay, so that's the idea of Koopman theory is I can actually project into a functional representation of the data and potentially get a much better viewpoint or a much better approximation to the dynamics. So those are some ways to do it, but the way we're going to actually concentrate here on is on using neural networks, okay? And the idea, remember, just neural networks are interpolators. And so whatever your training data is, your neural network's going to work well as an interpolation. Typically, they suffer under extrapolation. And this is a quote from Stefan Malat, who is just one of the very best people in the world. I think this is his first sentence of his paper, Understanding Convolutional Neural Networks. And so this is, I think it's really important to keep that in mind. Okay, so here's what we're going to do. And this is work with Bethany Lush. So Bethany, what she did is she said, okay, I'm going to try to learn a coordinate system where I measure some nonlinear dynamics, and I'm going to learn a linear space in which the dynamics becomes linear. So what we started with was the pendulum, just a simple pendulum, the nonlinear pendulum. So theta double dot is equal to sine theta, okay? So you want to move from your input space, and what the architecture here is to learn a coordinate transformation, which is just a neural network, and that's the encoder, into a new variable, and then come back out to your original variable, that's the decoder. So it's just a coordinate transformation, but it's a nonlinear coordinate transformation that I have to learn. And what I'm going to enforce to learn this is that in this middle layer, once I get into this latent variable representation, that when I move from y of k to y of k plus 1, in other words, I take one time step, I want that to be a linear map. And if I want to take multiple steps into the future, I want it to be, matrix multiply. If I take 2 steps, it's k squared. So this object that I'm trying to learn is the Koopman operator, okay, which is an operator that advances the solution, let's say, delta t into the future, at least for this discrete time system here. So this is what Bethany did. She tried to train this, and we failed. So we failed for quite a while. And the reason I say obviously at the bottom is, okay, so I've failed a lot in training a lot of neural networks. And so it became obvious why we were failing. And why we were failing was the fact that if you actually look at the dynamics of the pendulum, or I even study like a Duffing oscillator, which has a weak nonlinearity here, cubic. One thing to note is this, by the way, these are my grad student notes. I scanned them in because I wanted to prove you, like I did asymptotics and perturbation. We used to learn that stuff back then. And I scanned these in and I said, look, if I have a little bit of nonlinearity on an oscillator, what does it fundamentally do? It does 2 things. Shifts the frequencies and it generates harmonics. And here is the asymptotic result of this. Notice the frequency shift here. I get an epsilon frequency shift, and I get at next order a harmonic being generated at the 3rd harmonic. So if I do a spectrogram of this, in other words, on the y-axis is the frequency, on the x-axis is the strength of the oscillation, notice, or the amplitude of the oscillation, notice the frequency shift here. So the frequency shift of that fundamental gets shifted. Here's the 3rd harmonic. Here's the 5th harmonic. If you keep going up here, there's a 7th harmonic and so forth. So the problem with this is that if I'm going to try to embed this in a 2 by 2 dimensional space, which is essentially we believe that, right, the pendulum is a 2-dimensional thing, theta, theta dot can parameterize it. But the fact is that you have a continuous spectrum. In other words, there's a continuous dependence on the frequency. And a neural network doesn't know that. And so it says, I need to encode all these frequencies. So you really need a very high dimensional neural network. But what we're trying to do is constrain it to the physics, the actual dimension of what the physics is. So we came back to this and said, okay, let's redo this problem. But now the linear operator that's here has to be parametrized by the frequency. So there we go. We parameterize it by the frequency. And once you do that, now you have it. Now you can say, I'm going to take this pendulum data. Here's the full nonlinear dynamics of the pendulum. And you can see that, in the middle, right, low amplitude, it's sinusoidal. But as you get towards the saddle at the top, you get the strong nonlinear oscillations. You can see the frequency or period shift here. And so, but what we did is we learned a transformation into a coordinate system where it was linear dynamics all the way out to that saddle. And here are your, in some sense, eigenfunctions of this transformation that get you from one coordinate to the other. So this is very encouraging because I can basically make the pendulum linear even for very strongly nonlinear oscillations in this coordinate system. We did a harder example, which is flow around the cylinder, which is, you take flow around the cylinder until it starts doing vortex shedding. And so these are your snapshots of the data. And what we did here is we actually first projected into a low dimensional space by doing the SINDy. And there's 3 dominant modes. And we took the time series of those dominant modes, and there's some nonlinear dynamics that happens there. And we embedded that in a linear space. So all of a sudden, we've turned this whole flow around the cylinder into a linear dynamical system. And so that allows you then to calculate eigenvalues, eigenfunctions, and have the entire dynamics in this representation. So it can be done. And here's the more surprising result. We built on this architecture, and this is work with Craig Jin. So what Craig did, he said, okay, let's take this and let's do much harder problems. And in fact, I'm showing you here on the right, his results on the Kuromoto-Shibashinsky PDE. So the Kuromoto-Shibashinsky is a hard problem. It displays spatial temporal chaos. So the dynamics are quite interesting and hard to really pin down and characterize. And the question was, could we find a coordinate system in which the Kurimoto-Shibashinsky behaves linearly. And in fact, Craig was able to do this. A much more complicated architecture going from the initial measurement space into a latent space. And so I encourage you, if you just look up his paper, right? So we map this over into this latent space. And in this latent space, the dynamics, we could parameterize it and make it linear. So in fact, here are some full simulations of the Kurimoto-Shibashinsky. And here are, in fact, this linear network model coming back through the decoder. And basically, we're able to very accurately model the full PD dynamics with a linear model. Okay. So by the way, there are a group of PDEs we know can be linearized, right? Berger's equation through the Kohl-Hopf transformation. That is like exactly, it's one of the few examples we can work out a linearization explicitly. But there's also the inverse scattering transform for completely integrable systems like KDV, nonlinear Schrodinger. And what this does is a numerical approach. So it's very much like the inverse scattering transform. It linearizes something like Kurimoto-Shibashinsky. Okay. So that's surprising, but also a really interesting result, I think. And by the way, everything I'm talking about, all the code, all the data, everything you want, you can just download it and you can train this network yourself and verify these things. All right, so linear models is one way to go about this. A second way to go about this is actually trying to build governing equations instead. In other words, allow the dynamics to be nonlinear, but let's also make them parsimonious. And so this gets us to this idea of finding a nominal representation of the dynamics. And the way we do this is with this sparse identification of nonlinear dynamics. And this is a really simple technique, ultimately. This is just going to be AX equal to B. That's all we're going to solve here. It's going to be an overdetermined system of equations. And we're going to solve that. And you're going to find that in that solution, we find governing equations. So remember, we're going to measure a system, and I don't necessarily know the dynamics. So I don't know what F is. So it's X dot equals F. But if I give you the measurements X, okay? So for instance, here, this idea is I give you some measurements. So I don't know what the true system was. I just give you data, time series data for X, Y, and Z. Well, you could produce the derivatives, X dot, Y dot, Z dot. So you've got X dot, you don't know what F of X is. So what we do is we say, well, let's make a library of potential terms that F of X are. So you build a big library of saying, well, I don't know, there's lots of different possibilities for the right-hand side. Let me just put in all of them into a library. So where do we get motivated from these libraries? Well, I have a bunch of books here on my shelf. I can pull all kinds of governing equations out of there and build that library with it. And then what I do is say that's the matrix A. The X dot is B, so I have AX equal to B at this point. And what I don't want to do is solve this with least squares. Because if I do least squares, it'll try to make all the coefficients here small as possible. It'll tell you that every library element contributes to the dynamics. Instead, we promote sparsity. We say, how few library terms do I need to reconstruct the dynamics? So through sparse regression, and the way we actually do this is through least square thresholding. We do not do lasso. It's pretty unstable, but the concept of lasso is right, but the algorithm of lasso is not very good. But through this sparse regression, you actually find, look, these are the only terms that remain. There's 7 terms. What are they? They actually are your Lorenz model. So you've basically taken the time series data and discovered the governing equations that produce them. You can generalize this. This is work Sam Rudy did when he was a PhD here. He took, here's a big class of PDEs, and he basically said, well, if I just give you the spatial temporal data discretized, could you find the PDE that generated them? And the answer is yes. In fact, here are these different PDEs we reconstructed just from the data. You know, and also what Sam did is a very careful job telling you how he discretized, how much noise it could tolerate, and so forth. But conceptually, you could really do this quite nicely. Okay, so here's an aspect of this which I think is really important, which is, notice in this modeling paradigm, I'm assuming I know nothing. I just take data and I'm trying to discover the physics. But in most cases, you actually know some physics. So you've studied the system. It's just that your model is not good enough to describe the data. So instead of starting from scratch like we did here, where I know nothing, you start off with whatever knowledge you have. And so you say, I know some of this physics has to be true. Okay, but I know also that this model I have, I'm missing some physics, or there's some discrepancies there. And so I want to try to figure out, what do I have to add to do that? What physics should I add here? And so this SINDy paradigm is trivial to execute in this framework. Why? Because if you know f of x, you can just simply move it to the left-hand side. And so it's the vector b that I had before, which was just take the time series, take its derivative. Now you say take the time series, take the derivative, minus f of x, and then do your SINDy regression. In other words, a library of potential terms on the discrepancy portion. There's nothing that changes. It's really trivial to put into this framework. So here's an example of this, of a real physical system. The top is a pendulum, double pendulum on a cart. Okay, and same with the bottom. And with the top, essentially, we gave that cart full physics knowledge of an idealized system. In other words, it knows where the masses are, but in fact, it doesn't have any model for, you know, the wind resistance, frictional forces at the joints. And because of that, it's unable to actually stabilize this pendulum because it has the physics is off. The model it has is off. But once you allow this thing to learn a discrepancy model, then it can sort of learn how to stabilize itself in practice. And there you go. So now it's taken its Platonic model of idealized physics and now learn the discrepancies it needs to be able to do things from there. Where this is particularly important is in what we're moving towards, which is the digital twins revolution, which is here a real robot on the right, and here's its CAD-based simulation. And if you're doing precise manufacturing, this CAD sim model is simply not accurate enough to represent this real robot. So what you really need is to start off with a base model, which is easy to do, your F equals MA model with all the masses. But then from data, allow this CAD-based sim model to improve its representation of the real system. And by the way, each robot's discrepancy model will be different. And so what you allow this thing to do is to essentially create unique, personalized robots in some sense, right? Digital twins that are personalized for each different robot. So I think this is where this kind of architecture can really play a very nice role. Okay, some final thoughts about this. A lot of where we've had success is in pretty good data and not too much noise. So I want to take this same paradigm and go to this limit of big noise and little data. So these aren't precise words, obviously, but you know exactly what I'm talking about it when I say, you know, big noise and little data, which means you're not going to have much data and it has a ton of noise on it. Now, what are you going to do for model discovery? So this is very recent work where we're able to use, so for those of you who have real data and not that much of it, or even is pretty noisy, this here is where you just want to let your ears perk up a little, because I think this, I'm super excited about this, and I think this is really a viable method going forward. Okay, so basically the idea is in the SINDy, what we did is we said, let's take some data, we build this library, so it's Ax equal to B, and all we did was sparse regression to determine the library coefficients. Now what we're going to do is we're going to do this same technique, build a library, we're going to set up this regression problem, but now what we're going to do is use a sparsely promoting Bayesian inference to actually pull out probability distributions of every single one of these coefficients. So we're not pulling out just a number, we're pulling out PDFs, and so that we can get some idea of the probability of inclusion for any one of these library terms, okay? And so our model too now would be drawn from these PDFs. So we don't get a model, we get right? A distribution of models, the distribution being governed by the data here. And so now you have also uncertainty quantification that comes with this, okay? So the steps for this, let me just go through them very quick. You build your library. So now we're going to say, go from your time initial to the time final. This is going to be your data, and then fit a model to it, which is your library, time its loadings. And there's a couple of steps here. One is to frame this conditional probabilities of your data given the loadings. Okay, normally what we assume for the noise is normally distributed. You can either formulate it here as a normal distribution or in a log likelihood form. Finally, we make an assumption about the probability of the loadings. And this is where it gets interesting, because the two loadings that we played around with here, or the priors on these, this is where the Bayesian prior comes in, which is we can either make like a spike slab model. The spike slab model basically says I have sort of a distribution with spikes, and the spikes are the non-zero entries of the library, and the rest is distribution is sort of like, most of the rest is normally distributed. So that's our assumption on the distribution, either a spike slab model or regularized horseshoe. So now what you have to do once you have these is now you do MCMC. And this is where it gets expensive, but with the MCMC, you can sample the posterior distribution and construct sort of the probability distributions of the loading coefficients of those libraries, okay? So here's real data, Link's hair data. Now, what's remarkable about this data, this is data collected from 1900s to 1920, yearly snapshots of the rough number of lynx and hares that were up in sort of the Lake Huron region. And, these are just really rough numbers. So there's very little data, in fact, 21 time points. And it's also very noisy observations. But amazingly, what this will do is this regression will actually build for you a pretty reasonable model. This is a place where most model discovery techniques completely fail. And here, with orders of magnitude less data and noisy, it actually gives you a pretty reasonable model. And here are the probability distributions of the coefficients in these terms. And so what it gives you is actually a pretty nice predator-prey model describing this evolution. What we essentially did with this data, by the way, is we actually, by hand, wrote down a model, right? These are those Lotka-Volterra type equations. And what this does is sort of more a principled way to let the data derive that Lotka-Volterra type structure, okay? So lots of different, it's super modular, flexible, adaptive, lots of innovations have come around it, from
control to multiscale physics, to putting in constraints, to looking at flow maps and Poincare cuts. There's all kinds of work that has come from this, because it's a really simple architecture and pretty powerful for model discovery. Okay, let me see here. All right, keep going. Dynamics and coordinates. So up to that point, by the way, I was assuming I was building a model in the variable I measured, but now I want to highlight one last piece of work on this, which is work Kathleen Champion did. Kathleen was a former grad student, and what she did is said, okay, we kind of cheated, which is we knew kind of what the right variables should be. What if you took data and you don't even know what the right variables are? How would you do this process? And so now we go back to the original slides in this paper, which is, here's this structure. I have measurements. I want to find a coordinate system in which the dynamics is sparse. So what we're going to do here, now that we have this SINDy paradigm, is we're going to say, let's jointly learn a coordinate system where in the latent variable space, my SINDy modeling is going to be applied. In other words, I want to move myself to a coordinate system in which I can parsimoniously represent the physics. Okay, so she did a great job with this. And this last one here, I want to just highlight this. So I could walk through, there's a bunch of work here, but this is the one that matters. You take a video of a pendulum. So your state space is video space, is pixel space, high dimensional. And from the video, what the coordinate system learns, so if I come back here,
from the video, it learns theta, theta dot. And then it learns theta double dot sine theta. That's what this thing does. It did not know that the pendulum had this representative coordinate system of theta, theta dot. It learns that for you and makes the transformation. So here's the idea. That's my data. It does not know that that's a pendulum stuck to a wall and that the angle matters there, right? We, of course, look at it and know that, oh, that's a pendulum. And okay. But what it does, it learns the right coordinate system. It says, I know the coordinate system now, and now I can discover the physics. So this is a really powerful discovery paradigm because it not only finds the coordinates, but then says, and here's the physics that's actually happening there, okay? By the way, we can even go one step further. For those of you who really love dynamical systems, and I'm one of those, you can even go further. So even if you have these parsimonious representations, you could even say, well, actually what I'd really love to do is even discover sort of the underlying canonical form of the dynamics there, especially of a parametric dependence and instability. So you can embed this instead in a normal form. So very much like what Kathleen did, this is Manu Kalia, who's actually in University of Twente in the Netherlands. He came and visited for a while, and we were able to say, let's take these dynamics, especially as they walk through bifurcations, let's actually learn a coordinate representation in which it falls into one of the canonical normal form styles. And so this gives us a really beautiful way to represent things because now we have the right coordinate system in which we have the underlying instability mechanisms of that system. And there's not that many instability. I mean, this really goes back to pattern forming system. Pattern forming systems, one of the exciting things from that in the 80s and 90s was to realize that all these instabilities we see in nature are pretty canonical in their form. And so we're basically learning that as we go here. A couple comments, learning the coordinates. Once I have those coordinates, that's not generalizable, but often the physics model I learned there is, okay? So if I learn F equals ma, then that works for planet Mars and planet Saturn, except for the coordinates of Mars and Saturn are different, right? Mars is much closer to us than Saturn is. So this is not generalizable, but this physics concept is. Okay, let's keep going then. Okay, so mostly if you've seen here what I've been doing, I've been mostly working with the concept of figuring out a spatial warping of coordinates in order for me to find a really good representation, either make a linear model or a parsimonious model. Instead, I could just simply say, well, what if I were to, instead of that, warp the time series itself? So I have some temporal evolution. That's what I'm trying to actually build models on. What if instead I were to say, let me try to take a neural net and take this time series, which could be nonlinear dynamics, and make it look like sines and cosines. In other words, make it look like it's coming from a linear model. So this is exactly what Henning Lange did. He said, I'm going to try to basically take this and say, I could represent my time series in terms of sines and cosines. That's what this model here, that's a Fourier representation. And by the way, this is different than a Fourier transform in the sense that Fourier transforms, right, are constrained in their frequencies by whatever the domain is. And they have periodic boundary conditions. So if you have signals that are not periodic in that box, it will try to construct them to be periodic by using many more Fourier modes than you need. Okay, so he can learn a gradient descent algorithm to fit the best sines and not only learn the frequency, but make it so it has, you can fit it in boxes that are not periodic. But he also said, let's learn a neural network to take any time series, like for instance, this one here, which would require, it's very spiky, so it requires lots of Fourier modes. Say, no, let's transform this to make this look more sinusoidal. And then I use a very nominal representation of frequencies to get this. And then with that, we can do forecasting. And in fact, one of the things I want to highlight here is if you use these physics type knowledge, in other words, we know that sines and cosines are fantastic functions for long time forecasting because as you take them to infinity or minus infinity, they don't blow up. they don't go to zero, right? They stay between 1 and -1. And so when you start doing long-term forecasting, I just want to show you how this works on some real power grid data and comparing it against the leading state-of-the-art neural network methods. So here's our Koopman forecasting method. Here's the error up here, but LSTMs, GRUs, echo state networks, none of them can do as well. This beats all of them. And also we compared it against quite a few other of the standard statistical methods that are out there, you know, ARIMA models and so forth. And so basically this thing is just a really powerful tool, partly because you're doing the right thing, right? You're just saying, look, transform this to sines and cosines. This is the perfect basis for long-term representation. And then this gets it for you. Where this becomes really interesting too is in building models like reduced order models, which is I could take this cavity flow here. And so here's the full PD simulation. And this is the dynamics of this. I can look at some low dimensional embedding by just taking the SVD and saying, hey, there's some low dimensional representation of this. And the time series of that low dimensional representation, I can now do this Fourier forecasting trick. And now I can represent the future state of this trivially. You just tell me what time do you want the solution? I build you the solution. And look how accurate this is. This is quite remarkable. This is an amazing job. And it's super stable, unlike many of the projection-based raw methods, which can often lead to instability and blow up of solutions. Okay. All right. So by the way, there's no need to also be constrained by neural nets having, you know, this time stepping that I've shown you here. You can also just learn flow maps, right? And this is something interesting where you can say, hey, what if I just start learning flow maps? I just want to take my solution from time t and learn a map from time t to t plus delta t, where delta t is not necessarily small. So this architecture here, right? If you've taken numerical courses and you learn how to do numerical integration, right? This is like your basic, you know, Runge-Kutta, right? Except Runge-Kutta, Euler, almost all the stepping algorithms, delta, they're all based on Taylor expansions, which means delta t has to be small in order for this to be accurate. What if instead you just say, look, take neural networks and have them learn network mappings between one time and another? Well, delta t is not constrained to be small. So this is what Yu-Ying Liu did. And what he said is, well, how about I do one thing further, which is, how about if I learn a hierarchy of flow maps? So learn big steps, medium steps, small steps. So there's 3 neural networks being trained simultaneously. One, this blue one here, which is a big step into the future, this medium step into the future, and this small step into the future. And so by doing this, you actually start to decompose spatial temporal data into really nice features that are happening for you. In fact, if you want to do long time prediction, then what you do is take a couple of the really big steps out into the future, and then you refine it using your small and medium steps. So for instance, if I want to end up at x of t here, I'd first take one big step into the future, one medium step, and then 2 small steps. And I'm going to give you the prediction of the future state right there. So let me show you how well this works, because this is kind of remarkable. So here's 4 examples, 2 of them with physics, and the others don't really have physics, but we have chaos equations, flow around the cylinder. Here is this method, the hierarchical time stepping in terms of reconstructing the ground truth, and compare it against LSTM, echo state networks, some recurrent neural networks. So these are the sort of the state-of-the-art methods. But you can see that actually, if you actually compare the errors, it's really quite better by using this hierarchical time stepping. And you know, the LSTMs, all the neural networks do even really terrible here. This is just basically a music score, right? And look how well this does to reconstruct it versus these networks. So anyway, it's an interesting way to start thinking about doing numerical time stepping. You can what Yu-Ying also did is also not only did he do multi-scale in time, but he also thought about multi-scale in space. So you could start thinking about, you know, one thing that we've developed is a lot of multi-grid methods. You know, how do you how do you refine space-time? Well, what we can do here is set up a transfer learning paradigm where you first do a very coarse-grained model using some convolutional window to build a model for the spatial resolution. And then you look at your error and you say, wherever I'm getting large error because I have bad representation, I refine it just there with a smaller convolutional window. So I can keep this refinement process, and I take the neural network that was a previously, and I use that, transfer that next to the next level. So I don't just start this from scratch. I'm basically starting, I have a warm start to this by the transfer learning, and it's very similar to a multi-grid method where you refine where you need to build yourself a hierarchical structure for representation. So neural networks have a natural way of handling this. And so, you know, it's certainly a viable method, again, related to computation. Some final thoughts here are around boundary value problems. Almost everything I've talked about involves time, right? So I typically think about dynamical systems, but all these methods can be lifted to boundary value problems. So for instance, what Dan Shea did is he said, well, this whole discovery process of learning coordinates and learning dynamics, now we're going to say learn a coordinates and learn a boundary value problem. In other words, can I take measurements of a BVP and learn the governing equations of the BVP? And in fact, you can bring this whole SINDy architecture into that, and you can learn boundary value problems through this process, right? And so that's one of the things. In fact, more recently, what we did here, and this is something I really like, partly because I studied it a bunch in grad school. Green's functions. Green's functions are this really powerful solution technique that, you know, if you study mathematical physics, the Green's function features prominently throughout mathematical physics, but it's inherently a linear method. It relies on linear superposition. And a lot of the problems we study today are nonlinear. So, you know, Green's functions sort of, in some sense, have been thought to run their life. The linear problems, that was from the last century. Now we're doing all nonlinear all the time. But what this can do is say, well, what if I learn a coordinate transformation? So I'm going to take this boundary value problem, learn a coordinate transformation in which the BVP is linear. Now I can build a Green's function in there and construct solution. Now I have linear superposition holding. In fact, we call this Deep Green. It's up on the archive, and Deep Green allows you to do it. It just basically learns a coordinate transformation and learns a Green's function in this coordinate system. So now you can basically use all of the Green's function technology, which is you get a new forcing, then you can just say, and here's your solution. You have the fundamental solution computed already for that. Oops. All right, so that's kind of the end. Basically, I started here. I try to keep coming back to here, which is coordinates and dynamics, or coordinates and models, should be learned jointly. And really this idea that parsimony is sort of this ultimate physics regularization tool we use, which allowed us to be pretty successful in this sort of discovery paradigm. So anyway, I'll stop there and then we can go to questions or anything like that.
Thank you, Nathan. I'll stop recording so we can have it discussed.